Now we discuss about torsion of non-circular sections or bars having non-circular cross sections. In the previous semester, you studied the torsion of bars having circular cross section. Here we are going to discuss about the torsion of prismatic members, which is having a non-circular cross section. In the case of circular bars, we obtained the equations for angle of twist and the shear stresses. Here we consider a bar having circular bar having length L, and which is a torque T is applied at this end, and this end is fixed, so there is no rotation here. And here the point P is moved from here to P dash due to torsion, due to the twisting. So the total rotation here in this end is given as theta star. So for whole length the twist is theta star, so the angle of twist per unit length theta or theta star by L is given by the equation T divided by G into IP, where T is the torque applied and G is the shear modulus, and IP is the polar moment of area. Also obtain the equations for shear stress at any point on any circular cross section normal to the longitudinal axis. If we take a circular cross section here, a cross section normal to the longitudinal axis here, we can calculate the shear stress at a point on this circular cross section here. Okay, that is, the equation is given by tau is equal to T into R divided by IP, where R is the distance of the point from the centroidal axis or the axis of twist, and it is given that the direction of the shear stress is perpendicular to the radius, or it is in the tangential direction. Where will be the maximum stress? Maximum stress will be at the point on the outer surface or in the curved surface of the bar, and that is given as, if R is the radius of this thing, radius of this circle, tau max will be T into R divided by IP, and this will be directed tangential to the surface. Tau max will be directed tangential to the surface. Here, while deriving this equation, we assumed that the plane sections, we had an assumption, that is plane section before twist, the plane sections before twisting or before the application of the torque remains plane even after the application of the torque, or even after twisting. So there is no distortion during twisting, so plane section remains plane. Any cross section, if you take any cross section, that will remain plane during twisting. That is the assumption we made during the while deriving these equations. And if we use the same assumption for bars which is having non-circular cross section, we get erroneous result. For example, in the case of rectangular bar, if we use this assumption, we get maximum shearing stress at points further from the center of twist, as in this case. Which point is farthest from the center of twist? That is the corner points of the rectangular section. So but that is inconsistent with the boundary condition. To satisfy boundary condition, shear stress at corners of that rectangle should be 0. Okay, if we apply a torque on a bar having rectangular cross section, having as shown in figure, if we apply a torque here, and if we prevent this from twisting, prevent this face from twisting, we will get a shape like this. So here this face is prevented from twisting, and this is twisted to get this shape. But in addition to this twisting, we can also note that in this case here the rectangular faces will no longer be plane. If we take any section, if we take this section, for example, if we take this section or this section or any section, we can, or these end sections, we can find that there is a displacement, there is a distortion in the face, in the rectangular face. That is, if we take this, we can see there are distortion like this, and there are ridges and values on the faces, rectangular faces. If we mark these faces like this, we can see that any face for having, if we take this line, that will be distorted like this. So there is a displacement in z direction, or a parallel to the center of axis of twist. So this is called, if we take this section here also, we can find there is a twist here. Here also we can find twist like this, maybe something like this. So this is called warping of the cross section. This is called warping. Oh, that is the distortion of the plane sections before twisting, due to twisting the plane sections perpendicular to the center of twist distorted, and there is a displacement in, if it is the z direction, there is a displacement in z direction, if z is the longitudinal direction. Okay, that is called warping. Now we can start with the Venant's theory. He was the first person, Venant was the first person to obtain the correct solution of the problem of torsion of non-circular bars where couples are applied at ends. He used a semi inverse method. The method is called semi inverse method because he made certain assumptions about the deformations of the twisted bar, and he showed that after that he showed that these assumptions satisfied the equations of equilibrium and boundary conditions. So started in the semi inverse method, we started with the assumptions about deformation, and this satisfy deformation. After that we show that the deformation satisfy boundary conditions and differential equations of equilibrium equations. If the assumed deformation satisfies the boundary conditions and equilibrium equations from the uniqueness theorem, we can say that these deformations gives the solutions for the problem, the torsion problem. Here he assumed that the deformation of the twisted bar is of there are two types of deformation. The first one is deformation are two types. The first one is the the rotation of the cross section as in the case of circular bus. And second was the warping, which is the distortion or displacement in the direction of longitudinal action. The warping, he assumed that warping of the cross section which is same for all cross sections. Now we can consider the torsion of a non-circular section like this, and a torque T is applied at this end, and the x, y, z axis are shown like here. Z axis is the angle of axis of twist, and due to this torque, according to Venant's theory, there will be two parts of deformation. Means the deformation will be consists of two parts, that is the rotation as in the case of circular section, that is shown here, a point P, that is here we take as cross section at z distance from here. If theta is the angle of twist per unit length, the rotation of this point will be theta z, since the distance is shown here is z. So if we take any line, that will be rotated by theta z length, is theta z angle. Okay, so here that is shown here, and there will be another deformation, that is the warping, and we will discuss about that later. And this is this deformation is drawn here. The point initially having x and y coordinates, so this is this distance is x, and this distance is y, and due to torsion there is a displacement of point P to point P dash. Now here the displacement component in x direction is ux, which is in negative x direction. There is a displacement in y direction, that is uy, that is in positive x direction, positive y direction. So we can write that ux is equal to minus, okay, here this length, what will be this length if this is given as r? What will be this length? This will be r theta z. Okay, from trigonometry for small deformation we can say like that. So this will be r, here it is angle is beta, and for small deformation this also will be beta, and we can say that ux is equal to r theta z into sine beta. We have uy is equal to r theta z into cos beta, and from the figure we can get that sine beta is y by r and cos beta is x by r. R is this length from this point to origin to P, that is. So here we can, from that we can get here sine beta is equal to y by r and cos beta is equal to x by r. So we can say that ux is equal to minus theta into yz, uy is equal to theta into xz. And according to Venant, we know that for any cross section there will be a deformation in z direction. If we take any cross section, that is same. Venant assumed that warping is same for any cross section. So we have uz, that is a deformation in z direction due to warping, that is given as, he assumed that is theta into psi of xy. Why there is no z? Z is here, so it because it is for any z value we have same warping. For any cross section we have warping. For any cross section the warping is same, or the distortion is same for any cross section. Okay, now this is called psi is the warping function. Psi is the warping function. Okay, now from this displacement we can calculate strain components. Okay, we have ux, uy and uz. From this, how to calculate strain components? We can get that epsilon x is equal to that is dou ux by dou x. Okay, here we will get that is 0. There is no x term here, and we have epsilon y is equal to dou u y by dou y, that is equal to 0, and here uz is independent of z, so epsilon z also will be 0. Similarly, here we have shear strain gamma xy is equal to dou u x by dou y plus dou u y by dou x, that is equal to, here this term will give minus theta z, and next term will give plus theta z, so this also will be 0. So here these 4 strain terms are obtained as 0. Now we can obtain tau xz, that is equal to dou u x by dou z plus dou u z by dou x. Okay, here now we have dou by dou z of ux is given as minus minus theta y z plus dou by dou x of, here uz is theta into psi. Okay, psi is a function. So here theta is angle of twist by unit length is constant, so what we will get is gamma xz is equal to theta into dou psi by dou y, sorry, dou psi by dou x, here it is dou psi by dou x minus y. Similarly, we can obtain gamma yz, that is given as theta is into dou psi by dou y plus x. Okay, now we have only 2 strain components. Other strain components are 0. If we assume it is a linearly elastic material, we can apply Hooke's law. So since epsilon x, epsilon y and epsilon z are 0, we can directly write, you have studied Hooke's law earlier, from that we can directly write sigma x is equal to sigma y is equal to sigma z is equal to 0. Since only normal strain components contributes to normal stresses, and all normal strain components are 0, so normal stresses will be 0. And since gamma xy is 0, we can also write that tau xy equal to 0. And the other strain components, other stress components can be written by the relation tau is equal to g into gamma. Oh, we can write we have tau is equal to g into gamma. Oh, from that we will get tau xz is equal to, we have gamma xz like this, so tau xz will be g theta into dou psi by dou x minus y, and tau yz can be written as tau yz is equal to g theta into dou psi by dou y plus x. Now we obtained the stress components for this case, or the torsion of non-circular bars, and this represents the stress distribution in the body. These stress components that must satisfy the differential equations of equilibrium. So now we are going to write the differential equations. We have three differential equations of equilibrium, that is dou sigma x by dou x plus dou xy by dou y plus dou xz by dou z equal to 0. If there is no body force, we can, in this case there is no body force, so we can write like this. Here tau xy by, now we are using complementary properties of shear, dou sigma y by dou y plus dou yz by dou z is equal to 0, and the third equation is dou xz by dou x plus dou yz by dou y plus dou sigma z by dou z equal to 0. Here we know that sigma x is 0, so this term will not be there, and tau xy is 0, so this term also vanishes, and this, and since sigma y is 0, this term also vanishes. So the first two equations are identically satisfied. So the only equation left is the third equation, and in this equation, since sigma z is 0, there are two terms, so we can write these equations. We have tau xz is g theta into dou psi by dou x minus y. Tau xz is equal to g theta into dou psi by dou x minus y. Okay, so tau xz by dou x will be g theta into dou square psi by dou x square minus 0, and we also have tau yz, that is g theta into, here we will check here, g theta into dou psi by dou y plus x, dou psi by dou y plus x, tau yz divided by dou y, we will get g theta into dou square psi by dou y square plus 0. So if we substitute these values in this equation, what we will get? We will get g theta into dou square psi by dou square psi by dou x square plus dou square psi by dou y square is equal to 0, or since g theta is not 0, we can write dou square psi by dou x square plus dou square psi by dou y square, or we can write this as del square psi equal to 0. So the warping function psi satisfies Laplace equation, or satisfies Laplace equation, or we can say that psi is harmonic over the whole area or whole region of cross section. So now if we take any area of any area, that is any cross section, that is rectangular, maybe rectangular, triangular, or elliptical, or any other irregular shape, in all those cases the warping function should be such that it is an harmonic function. So now we will move into boundary conditions. So the stress components that we have already calculated must satisfy that boundary conditions also. The boundary conditions gives the relationship between the applied stresses on a point, the external forces on a point, to the stress tensor, which is a continuation of the internal stresses at that point. So if we have a point on the boundary which is having the surface having a direction cosines that is given by n is equal to surface having outward normal, which is nxi plus nyj plus nzk. Here nx, ny and nz are the direction cosines. N is the unit normal vector. Stresses due to applied forces at that point are given by tx, ty, tz. These are the x, y and z components of the external stresses applied on that point of the surface. So the boundary conditions are we have three boundary conditions that are given like this: sigma x into nx plus tau xy into ny plus tau xz into nz is equal to tx. So xy into nx plus sigma y into ny plus tau yz into nz is equal to ty, and the third one is tau xz into nx plus tau yz into ny plus sigma z into nz is equal to tz. These are the boundary conditions. But in this case, here if we take the cross section, which is if we take the body which is under the tension, if we take any cross section, or if we take the surface, here there is no forces acting on the surface. Okay, there is no tx, so tx, ty and tz are 0, and there is tx is 0, ty is 0 and tz is 0. We also know that sigma x is 0, tau xy is equal to 0, tau xy sigma y is 0. So these first two equations are identically satisfied. The only one equation left is this, and here sigma z is 0. So the only boundary condition now we are going to look is tau xz into nx plus tau yz into ny is equal to 0. This is the only boundary condition. Now we consider any cross section. Here if you take a point on the boundary that is having delta, a small point on the boundary that is having delta s length, and this is a delta s length, and this is delta x, this is delta y, and if you take a small triangular prism, and this is the outward normal, okay, which is represented by direction cosines nx, ny, and here we have nx, ny, and here it should be nz should be there, and it is actually 0 if we take any point on the surface. That is, if we draw any point on the surface. Here we have z-axis like this. So if we take any point on the surface that is perpendicular to the outward normal will be outward normal from the surface will be perpendicular to z-axis, so nz will be 0. So nx and ny will be there, nz is 0. So we redraw this here. Delta s, this is delta s is here, delta s is here, and we have delta x and we have delta y. So if delta s is increasing from this point to this point, this will be directed like this. So if we show delta x, this will be negative delta x, and this is positive delta y. And if we have normal, n is like this and it is unit normal, so the direction with cosine will be its x and y components will be its direction cosines. This is nx and this will be ny. If this angle is alpha, we can show that from trigonometry this also should be alpha. So here we will get nx, we will get the values of direction cosines, that is nx is equal to delta, that is cos alpha, nx is equal to cos alpha, that is delta y divided by delta s, and ny is equal to sin alpha, that is delta x by delta s. Here a negative sign is there since it is delta x is directed like in this direction. So apply limits, or if we shrink this length delta s to a point, okay, now we will get the boundary, we will get nx as dy by ds and ny as minus dx by ds. So now the equation can be written as tau xz into nx plus tau yz into ny is equal to 0. That is the only boundary condition left. We have the equations. We have the value of tau xz, that is tau xz is given by g theta into dou psi by dou x minus y, and tau yz is given by g theta into dou psi by dou y plus x. So and nx and ny is calculated here. nx is dy by ds and ny is minus dx by ds. So the boundary condition will be dou psi by dou x minus y into dy by ds minus dou psi by dou y plus x equal to into dx by ds equal to 0. Here g theta 10 will be cancelled. In both terms we have g theta term, and since it is here it is 0 and we know that g theta is not 0, we can write the equation like this. So each problem of torsion is reduced to a problem of finding a function psi which satisfies this equation, which is the boundary condition, and which is a harmonic function. So the problem is reduced to finding SI which satisfies these two equations. This is called Venant's formulation, and if we look into the boundary conditions, we can see that it is very difficult to obtain a solution for practical problems. Even though it is very difficult, Venant obtained solutions for a great number of problems, and in the next session we will look into solution for circular and elliptical problems.